This is the second example of orthogonally diagonalize the matrix. So here is our matrix A. We want to find a matrix that contains the normalized eigenvector to this matrix A. That's what they're asking. One more time. We want to find a matrix that has the normalized eigenvector to this matrix A. So step one, we will transpose A. So column to row, column to row, column to row. And as you can see, the original A and the transpose A are symmetric. Okay. Next, we need to find the determinant of the original A so that I can get my eigenvalue. Okay. Now there's going to be a lot of steps that I am skipping so that the video will be short, and I am assuming you know how to get them. All right. Again, there's going to be a lot of steps that I am skipping. So here's the original A. This is my I matrix using lambda all the way down to the diagonal. The rest is just 0. Now just add, subtract across, and that's what I have. This is a 3 by 3. So I'm going to use cofactor so I can find my polynomial, which is over here. So cofactor, I'm going to block this column, block this row, and I just have this portion right here, which is here. So this times this. Okay. Next, block this column, block this row, block this column. So I have 1, which is here, and then 1, 5, 1, 1 minus lambda, which is here. And then after that, it will be a plus. So plus minus plus. So if you remember cofactor, block this row, block this column. I just have this portion left with the 5. And that's what I have here. After that, cross multiply, minus cross multiply to each of these. Multiply them all out, combine like terms, and then you will end up this polynomial with lambda to the third power minus 7x squared minus lambda squared minus 16 lambda plus 112. Okay, so again, where did this polynomial came from? From using cofactor. Okay, if you remember cofactor. All right, so that's where this polynomial came from. Okay. After that, I will use the factoring. So I hope you remember synthetic divisions from maybe pre-calculus class, which is Math 110. So using synthetic division, either Math 105 or 110, and maybe both classes. All right. So using synthetic division, again, I'm going to shortcut this to go straight to the point because I don't have time to go through every single term. So I'm just going to do 1 minus 7 minus 16, 112 using the coefficients right here, using the coefficient terms. After that, I'm going to use 7 because 7 will give me my factor. So 7, all right, so bring down the 1. 7 times 1 gives me 7, subtract gives me 0. 7 times 0 is 0, so add, subtract gives me negative 16. 7 times negative 16 gives me negative 112. Add, subtract gives me 0. If this right here is a 0, then we know that 7 is a factor. One more time. When you use synthetic division, if this right here is a 0, then this divisor, this number that you're dividing, is a factor. And when it is a factor, make sure you do the opposite because this is plus, so over here has to be a minus. Next, this right here will be your x squared. This right here will be 0, and then you have negative 16. The reason why I don't put a 0 here because there's no point. Okay. After that, factor this out right here. The x squared minus 16 is just technically x minus 4, x plus 4. Okay, so these are our factors, and opposite of that will become your eigenvalue, which I have up here. Okay, again, where did I get this polynomial? Using the cofactor of this 3 by 3 matrix, multiply everything out, combine like terms, and you will get this polynomial. After that, I use synthetic division so I can get my factor. So these are my factors. Okay, and I hope you remember synthetic division back in college algebra, which is Math 105, and maybe Math 110, which is from pre-calculus. Okay, so these are our factors, and do the opposite of it. So it becomes -4, +4, +7. So these three are our eigenvalue. Now take these three to go get my eigenvector. Okay, so again, I'm gonna shortcut this to make so that the video won't be too long. So here is our eigenvalue for -4. If you remember, again, I'm skipping a lot of steps, so you should know how to get the eigenvector. So this is the eigenvector correspond to the eigenvalue. Same thing with +4, same thing with +7. So know how to go through, get the eigenvector for each eigenvalue. Okay, so this right here, this eigenvector 1, vector 2, vector 3, this right here is just the regular eigenvector. Over here is the normalized eigenvector. Okay, so this right here is our regular eigenvector. This right here is our normalized eigenvector. So there's a difference. Okay, and then after that, these three right here is what we are looking for. Okay, this is what we are looking for. All right, so vector 1, normalized eigenvector 1, normalized eigenvector 2, normalized eigenvector 3. Put that together, and that will become our matrix that we are looking for. Okay, this matrix is our eigenvalue. All right, so again, we're going to short this down. So we'll just assume that this right here, the normalized, this right here, the normalized, right here, the normalized, and the orthogonal normalized, and the spectral decomposition are true. So I'm going to short this down so that the video is not too long. But if you can, try to do that on your own, and it will come out the answer. Okay, so one more time. This right here that I am circling, this is the diagonalized. This over here is the orthogonal diagonalized. All right, and the spectral decompositions from the previous example, previous video. So we'll just assume that it is true. Okay, so again, if you are going to do diagonalize, then you will use regular eigenvector. If you're going to do orthogonal diagonalize, then you will use the normalized eigenvector. Okay, so these right here are regular eigenvector. So this is for diagonalize. This right here is the normalized eigenvector. So this is for orthogonal diagonalize. Okay, so go back to here so you can see the difference. This right here is diagonalize. This right here is orthogonally diagonalize. And then spectral decomposition. So all three methods, we'll just assume that it is true for now. Okay, just to save time of recording. Right? So this is the answer that we are looking for to represent A. Okay, so this right here is the orthogonal diagonalized matrix that we need to satisfy this matrix A.